Welcome all. It is my great pleasure to introduce our speaker for today, Nicholas Loizo, who comes to us from actually, I think, well, at least warm and rainy Cyprus right now. He's spending a few days or a few weeks, I guess, in Cyprus. But he's currently a postdoctoral research fellow at Mila at Université de Montréal. He finished his PhD studies with Peter Richtaric at Edinburgh, the School of Math, and he also has other degrees in mathematics from National University of Athens and a master's from Imperial. He's a superstar up-and-coming researcher in the intersection of optimization with application in machine learning and data science. He's won many awards, including the OR Society's 2019 Doctoral Award, runner-up for the most distinguished body of research, and also an Ivado postdoctoral fellowship. So I'm going to turn it over to Nicholas, who's going to tell us about large-scale optimization for machine learning and data science. I guess I should say, if you have any questions, I prefer that you actually, well, I'll be monitoring the chat. So clarification questions, you can feel free to post in the chat and we'll interrupt Nicholas if need be. And then of course, there'll be lots of time for people to answer questions at the end. So with that, please take it away, Nicholas.
Hi, thank you very much for having me here. It's a great pleasure to see many familiar faces in Madison. So I have opened the screen with all of you in the second screen behind, so I can see all of you. If you raise hand, I can answer a question. I have the chat as well. So as you can see from the title, today I will discuss on some of my recent results and the recent progress on solving large-scale optimization problems that appear in machine learning and data science tasks. So a brief overview of the talk. It will be mainly divided in four main parts. In the first one, I will briefly introduce myself, explain what are my research interests and my research expertise, and what is my thought process on making a contribution in the area of machine learning and data science. Then I will go into the main part of the talk and explain why optimization is fundamental for machine learning and provide the basic formulation that we are interested to solve, and explain why the stochastic optimization algorithm should be our go-to methods for large-scale problems, the ones that appear in machine learning and data science. And I will close the background section with a quick overview of some of my work in this area. Then I will go into the more technical part, where I will present a recent analysis, general theoretical analysis, describing the convergence of AGD under the arbitrary sampling paradigm, and also provide a new novel adaptive method for solving finite sum problems, which is the SPS optimizer, and is a stochastic variant of the classical polyak step size in the update of AGD. We propose a stochastic variant of the polyak step size. Then I will close the key contributions, and if the time allows us, I will explain why stochastic optimization methods can be also solve stochastic smooth games, min-max optimization problems through a Hamiltonian viewpoint. And I will close the whole talk with the future research directions that I'm planning to pursue in the next 4 to 5 years. So a brief overview about me. Jeff explained that before, but let me briefly tell everything research-wise. So I obtained my first degree in mathematics in Athens, and then I moved to the UK, where I obtained my master's degree in computer science from Imperial College London, and my PhD in optimization and operation research from the University of Edinburgh. In my PhD, I mostly focus on the development of randomized iterative methods for solving large-scale linear systems and structure convex optimization problems. While I was a PhD student, I was also research intern at Facebook AI, where I work on distributed algorithms for training deep neural networks. At the moment, I'm at Milan Université de Montréal, where I'm focusing mostly on non-convex optimization and its applications for deep neural networks. So I will say that my research interests can be divided in three main categories, three different research pillars. The first one is stochastic optimization, which itself is divided on randomized numerical linear algebra, developing of methods for solving linear systems, convex feasibility problems, problems appearing in scientific computing, but without having in mind machine learning. Then the second part is stochastic optimization, specifically designed for solving convex and non-convex optimization problems that appears in machine learning tasks. A big part of my research is also devoted on distributed and decentralized algorithms, in particular for solving problems that appear particularly in control theory and signal processing, and recently for proposing algorithms for solving problems mainly from the federated learning regime. A recent addition to my research interest is the algorithmic game theory, and in particular, developing of algorithms for solving adversarial formulations appearing in machine learning, min-max problems or two-player problems, mainly inspired by GANs. So, as a summary, in one sentence, I focus on the design, complexity analysis, and efficient implementation of stochastic optimization algorithms for solving large-scale problems. And the thought process of doing that is that we start from an application of interest, where we are able to formulate this as an optimization problem. Then the first step is to try that we spend a lot of time into it, is to understand the mathematical foundations behind this problem. What are the properties of the function of interest, and what are the fundamental limits of existing algorithms for solving these problems? And then we come up with efficient, resource-light alternative algorithms for solving this particular problem with theoretical guarantees. And after we have that, we release a software which the practitioners or other researchers being interested on solving this particular problem who will efficiently use it as a black box method without care about anything, just using the method that we provide. And now, having explained a bit of a background, let us go to the main part of this talk. So optimization problems are everywhere, appears in applications in finance, operation research, statistics, engineering. In all of these applications, we are interested in minimize a loss function or maximize our profit. Mathematically, this can be expressed as minimization of a function f of x, where x requires to satisfy some constraints. And of course, optimization is also at the heart of machine learning and data science. We require to solve optimization problems in visual object recognition tasks, in speech recognition and natural language processing, in personalized recommendation in advertising and marketing, of course, in image segmentation and sensor in autonomous cars, and the most prominent paradigm at the moment on training of deep neural networks. All of these applications can be solved, appear optimization problems in all of these applications that requires the development of optimization algorithms for solving them. Some more concrete examples, for example, in Netflix and YouTube, when you have a personal recommendation of your favorite movie or of your favorite video clip that you might enjoy, behind that, there is an optimization problem. In object and action recognition in images, when you train your model to recognize what appears in a picture, you train it using an optimization algorithm. Also, in applications like Siri and Google Assistant in speech recognition, and in computer vision like image segmentation and sensors in autonomous cars. And of course, in distributed and federated learning, when we have also to optimize the communication cost between the communication of the nodes of our network. All of these problems, and this is the main focus of my research, can be formulated as supervised machine learning models, where we have N observations, AI and BI, where the AI represents the input feature vector. For example, it can be the images in the classification task, in the object recognition tasks. And BI is its label. For example, if in the image there is a cat, in the binary classification task, this could be equivalent to 1, and if it's not a cat, it's -1. And our task in all of these supervised machine learning models is to compute the parameter x, which characterizing the model that best fits the observed data. And this can be expressed as an optimization problem, as a finite sum optimization problem, which is known as empirical risk minimization, where we have to minimize a function f of x, which is itself an average of functions f of I that depends on the n observations AI and BI, and we require to find this X that minimizes this function. And however, a common feature of this problem, the empirical rich minimization, the finite sum optimization problem, is that the parameters n, the number of features, and also the d, the dimension of the vector x, is very large. So classical methods like gradient descent or Newton method are very expensive, have a very expensive update, which means that we need to come up with new alternatives. This is where stochastic optimization methods comes to play. Let me explain why stochastic optimization algorithms and give a motivation of why this should be the go-to methods in this large-scale setting. Let us have the finite sum optimization problem, and then let's run the deterministic gradient descent. Here, in each iteration, we require to evaluate the full gradient of in each xk, which means that we require to evaluate the gradients of each component function fi in each iteration. Note that the iteration cost of the deterministic gradient descent is linear in n, which means that as n increase, then the iteration cost of each iteration cost is increased as well. However, in the stochastic gradient setting now, we require, in its simplest form, we require only the computation of one single component fi, and we require only its gradient. And we move towards the negative direction of this stochastic gradient in a distance that defines from this gamma k, which is a step size. Note that here the stochastic gradient is an unbiased estimator of the full gradient, which means that in expectation, we converge to the correct solution if you select with the correct way the gamma k. Here, note as well that iteration cost is independent of n. We don't care how many features we have. You just run SGD and you select one single component in each update. To understand better how these two methods behave, let's visualize it and let us run deterministic gradient descent with a constant step size. We know that we move to the negative direction, and in each, you know that after specific number of iterations, you will converge to the minimum point. Now in the stochastic gradient descent, in each iteration, you go to a random direction. And you know that if you select the step size to be a decreasing one, after a specific number of iterations, you can have an approximation of the solution because in general, you move towards the direction which is an expectation of the full gradient. And now the question is, when I should prefer a stochastic gradient method, SGD, over gradient descent? And the answer to this is when we have low accuracy time situation, which is normally the machine learning, the case in machine learning tasks that we're interested in. Note that if you have a limited time, then stochastic gradient descent is faster than the deterministic gradient descent. And also in machine learning tasks, we don't care of find a high accuracy solution of our problem. We care about find approximation, a neighborhood of the solution. So it's fine to run stochastic gradient descent. Of course, if you have the budget or the sources to run deterministic gradient descent, you can still do it, but it's very expensive. And now let me present the most general form of stochastic gradient descent, where in each step, we select an unbiased estimator of the full gradient. And we move towards the negative direction of this unbiased estimator. And we have the gamma k, which is the step size that defines how far you go from the current iterate. And as an optimizer now, we have several questions that we require to answer. For example, what is the convergence guarantees that we can have if we have specific assumptions on the problem, and what are these weak realistic assumptions that we need to satisfy in our theoretical results? What should be the step size selection based on the application that we have in mind? Should be constant, decreasing, adaptive? What is the optimum minimum batch size? How many components FI I should select in each update in order to guarantee the best iteration complexity? What will happen in over-parameterized models? And what will be the best unbiased estimator for selecting the update of selecting the update in each step? And what we will have if we add momentum on top of the unbiased estimator. And of course, what will happen in the distribution D when we select different distributions in order to select this unbiased estimator? All of these questions are interesting questions for an optimizer. Do not worry if you are not familiar with the terminology. Whenever I will define something in the following slides, I will define it properly, mathematically, and being clear. But when you have questions, feel free to interrupt me. And let me summarize some of these questions. Let me summarize some of the contributions that I made to answer them the last couple of years. So we have several papers focusing on the analysis, efficient analysis of AGD for solving modern machine learning applications. And in this talk, I will focus in 3 papers. The one is the general analysis of AGD and improved rates that appear in ICML of 2019. The other one is a stochastic polyak step size for AGD that will appear in AI Stats of 2021. And if we have time, I will cover also the Hamiltonian viewpoint of solving specific games that appears in machine learning tasks, and we are interested to solve it. Whenever the problem is too large, instead of solving it with a single machine, we select to do that with multiple machines, multiple computers. And this is where we are interested as well on decentralized or distributed stochastic gradient methods. Here we care about the communication cost. I will not cover that part in this talk. I will focus on these 3 papers, but I will be happy to discuss all the details of this direction offline or at the end of this session. So let me now go to the key contributions and the main part. So I'm good on time. So I will keep everything on high level ideas, but I will have some technical dives at some points. So again, feel free to interrupt me at any point if something is unclear. Let me first formalize the main problem that we're trying to solve. As I explained before, this is a finite sum optimization problem where we have to minimize a function f of x, which is an average of functions f of I. Here, x corresponds to the model parameters, n is the number of training data, and fi represents the loss on the training point I. X star, throughout the talk, we will assume that the x star, the set of optimal points of this problem, is not empty. F star defines the minimum value of f, and I will indicate with fi star the infimum of each function fi. I will assume throughout the talk that functions f and fi are smooth, which means that they have a Lipschitz continuous gradient, and I will indicate with L the one that corresponds to function f, and with Li the smoothness parameter that corresponds to functions fi. Depending on the model under study, these functions can either be strongly convex, convex, or non-convex, based on the applications that we have in mind. Okay. Let me give you a brief overview on the literature before I go to the main contributions of our work on AGD under arbitrary sampling analysis. So normally in the update rule of AGD, in the simple variant, in each step, we select with probability 1/n a specific sample of the finite sum of the FIs. However, there is a question that many people are interested in: if we are able to achieve faster conversions by selected different sampling, instead of selecting with 1/n probabilities, each one of the FIs, to select them with different probabilities. And the answer to this is to, yes, there are a lot of literature, and there are, the idea is to sample more important data more often. And this is, the solution to this is to sample with non-uniform sampling, or what is known as important sampling, which of course it has a mini-batch variant as well. Mini-batch here, as I explained before, is instead of selecting one single component FI in each step, you select multiple of them, and you compute the gradient of this mini-batch of components. There is a rich literature in the area of that first they define a sampling, and then they provide analysis of AGD under this particular sampling. However, there are many open questions in this area. For example, is it possible to provide an analysis of AGD under the arbitrary sampling paradigm, where whatever sampling you give me, a reasonable sampling, to provide you convergence guarantees? If we focus on the mini-batch setting, is it possible to obtain an optimal mini-batch size? How many components Fi you need to select in each step? Instead of 1, which is a single element sampling, and instead of n, which is a gradient, it turns out that it's something in between the optimum mini-batch size. And this is what I will explain in the following slides. And what should be the assumptions in order to guarantee convergence? The weakest possible assumptions. The main contributions now of our work is that we provide the first analysis for AGD under the arbitrary sampling paradigm, which extends, simplifies, and improves upon previous results in this area. As a byproduct of this analysis, we were able to provide for the first time an analysis of AGD that captures the gradient descent as special case. We were also able to provide a formula for the optimum mini-batch size and also have non-uniform importance sampling for mini-batch AGD. And for doing that, in our analysis, we get rid of all unreasonable assumptions on the second moment and on the variance of the stochastic gradient. Instead, we use a very intuitively assumption, which we call expected smoothness, that can be easily, that is a follow-up of convexity and smoothness. So if you have convexity and smoothness, you don't require any other assumptions to have the convergence guarantees that we will provide. Here I should highlight that papers that assume bounded gradients and also focus on problems that are strongly convex, it turns out that strong convexity with a bounded gradient contradicts each other. So if you have a theorem that have a bounded gradient and strongly convex function, you have an empty set of functions of the results that you provide. It doesn't hold. So this is what we need to get rid of because we find it unreasonable. So let me start with a stochastic reformulation of the finite sum problems, which is one of the new conceptual tool that we propose in this line of work. So we start with a sampling vector V, which in expectation, each one of its coordinates is equal to 1. And what we do is that to stochastic reformulate the finite sum optimization problem. The finite sum optimization problem itself is a deterministic problem, has no stochasticity. So what we do, we introduce this sampling vector, and by taking the expectation, we can see that we have two equivalent problems. The one is the original, the deterministic finite sum problem, and the other one, by doing this stochastic reformulation, we have a problem which can be expressed as an expectation of f of v. Note that this f of v is just a linear combinations of all fi's. However, by doing that, we were able to control the distribution D. And note that the expectation of the gradient of f of v is an unbiased estimator of the full gradient by taking simple computation of taking the expectation of the VI's. And what is our suggestion now is instead of running AGD to the original finite sum optimization problem, to running to the stochastic reformulation, which is the minimization of over random linear combination of the original functions. Which what we ended up is to have this problem, and we run AGD on this problem. So we sample the VKs from the distribution D, and we run AGD. In each step, we select one stochastic gradient, and we evaluate its gradient, one stochastic gradient, and we move toward the negative direction of this stochastic gradient. And why this is interesting and why we are flexible, why it's important? Because by varying the D, which is a user-friendly defined distribution, we obtain different existing and new variants of AGD as special cases. D encodes any form of mini-batch and non-uniform sampling as a special case by selecting it in advance. And with our analysis, we perform a convergence analysis of AGD for any distribution D. Just to get, Jeff, can I ask a question? So there is a chat question.
Oh,
Yes,
sorry. Yeah.
Oh, yeah, sure. Go ahead.
Nicholas, this is Steve. Sorry. Just a quick question. So this only is practical when the VKs that you choose are sparse, right? Because if they're,
yes, exactly.
if they're dense, you basically have to evaluate a whole gradient.
Yes, and that's exactly what I mentioned here as a simple example to show what it means. That if V is the vector of all ones, then you simply have the update of full gradient descent. But we always select it to be sparse in order to work on the large scale setting. That's correct.
Thanks.
And just another question on the V's. I don't,
Yes.
maybe you said it, but I guess they're non-negative random variables, right?
Yes, yes. So for the specific examples that we give, and special cases of the V are always non-negative. That's right.
I mean, would it even make sense if you allowed distributions that were not strictly positive?
I think it will not make sense.
Yeah, when you're mixing,
yeah,
you don't
should
have
be
that.
positive.
Yeah. Okay.
Yeah.
Good. Thank you.
Yeah. So, and just to give you a nice special case of our analysis, which is a tau sampling of uniform mini-batch AGD. In each step, we select in random, uniformly at random, a set of tau components Fi. And by doing that, we know that the probability of selecting one specific component I in this mini-batch size is tau over n. For this specific sampling, the VIs take the form 1 over pi, which is n over tau, where n is the number of all features and tau is the mini-batch size. And by replacing this value in the update of the stochastic gradient on the stochastic reformulation, you simply obtain the mini-batch AGD that we are all familiar with. And however, and note that if tau is equal to 1, then we will have the single element AGD, and if tau is equal to n, we will have the full gradient descent. And there is an impact of this stochastic reformulation in different areas as well. So at the moment, these ideas and this conceptual tool that we propose in this work, it was also used on linear systems and methods that you have the linear system, you reformulate it to a stochastic reformulation, and then you run methods with different samplings to solve it. And the same happened on the convex feasibility problems, taking the finite sum problem and use it for proposing optimum mini-batch size or different sampling on variance reduced methods and randomized coordinate descent. Now, let me go, having presented this stochastic reformulation, let me also go into the more details on the convergence analysis. As I mentioned before, we propose a novel assumption, which we call expected smoothness, and is the one given in equation 7. We assume through all of our results that the expectation of the norm of the difference of the stochastic gradient on x and x star is bounded by a times factor the function suboptimality. This is not a strange assumption. We show that it works and it holds. If FIs are convex and smooth, then this expected smoothness is satisfied. It's not an assumption that we have to assume in this context. So if you have a theorem where you assume that the FIs are convex and smooth, this is coming for free. You don't need it as an assumption. However, expected smoothness is also satisfied in several examples in non-convex setting, but we require smoothness. And this calligraphic L, which we will call it expected smoothness parameter, it lives between the L, and is lower bounded between the L, the smoothness parameter of the function f, and the maximum of the smoothness parameters of LIs. So this is the interval that this calligraphic L lives. And now we come up with a lemma that says that if the expected smoothness is satisfied, then you can upper bound the norm of the gradient and the upper bound will depend on the function suboptimality of the function f plus 2 sigma squared. Here, sigma is not an assumption like previously we have in all of the analysis of AGD. Sigma is only a specific quantity that depends on the optimum value. The only assumption that we made, and it's always satisfied in most of our problems, is that we assume that this sigma is finite. So by having this lemma and expected smoothness, we assume that the function is mu strongly quasi-convex. This is a slightly generalization of strong convexity that captures also some non-convex functions. If we assume that this function is f is mu quasi-strongly convex, and we assume expected smoothness, then by selecting the step size to be constant step size between 0 and 1/2L, this L is the calligraphic L of the expected smoothness. Then we can guarantee linear convergence to a neighborhood, and the neighborhood is proportional to the step size and this sigma square. This is a standard result that appears in all of the AGD analysis, but the important here is that this result holds for any possible sampling and holds under the weakest possible assumptions. And we show that in the paper. And now we have a corollary out of this, that if we have a given accuracy epsilon, and we're selecting the step size to be the minimum of these two quantities here, then we know that after a specific number of iterations, we can guarantee convergence to a neighborhood that is bounded from this accuracy epsilon. And this is the number of iterations. And having that in mind, we are able to construct the optimum mini-batch size. And the question that we need to answer is what should be the mini-batch tau in order for the optimum mini-batch size to be optimum, for the mini-batch size to be optimum. And this is the number of iterations. Here I ignore the logarithmic term that I mentioned before, this guy here. And we multiplied it with the mini-batch size. And the question is, are we able to somehow find this tau, and what is specific value of this tau? And we come up with this theorem that if we have tau-nice sampling, this is one special variant of all of our samplings that we have in the papers. If we have this tau-nice sampling, then the calligraphic L takes this form here. It's a convex combination of L and L max. And the sigma square take this form here. I will not go into the details on this. The important thing is to know that the tau, if tau is equal to n, then the calligraphic L is equal to L, and the sigma square is equal to 0, which means that we obtain the deterministic gradient descent, a special case of our analysis. And to the best of our knowledge, this was the first time that an analysis of AGD captures also the convergence of deterministic gradient descent as special case. There is one question, I think, in the chat.
Yeah, if you want to take Kartik's question now, just maybe get some intuition as to, because he's trying to understand the difference between strongly quasi-convex and not strongly convex.
Yes, yes.
Not strongly
so
convex.
the one example. So in terms of theory, I never seen a theorem that holds for strongly convex function. It does not hold for quasi-strongly convex. That's the first. So it's not that it's something important in terms of analysis. Now, in terms of application, I've seen some papers that they show that when you have a deep neural network, then the path of the points of AGD satisfy the strongly convex, strongly quasi-convex assumption. So all the iterations of AGD satisfy this quasi-strong convexity. And this is where I feel that is important. But besides that, it's just a simple generalization which you can have a larger set of functions that you can provide convergence guarantees. Kartik, did I answer your question?
Yes, thank you. Thanks,
Okay,
Nicholas.
good, great. So, and here with the optimal mini-batch size, if we replace this calligraphic L and this sigma that I mentioned before, we can see that the optimal mini-batch size is not 1, is not n, is something in between, and has this strange formulation here, which we went and computed in several logistic regression problems, and we ran experiments, and in all of them, we found that this tau star sampling, the one that we have, the optimum mini-batch sampling, has always the best performance. Here I just present some of these numerical experiments on simple logistic regression. We have it on real data, comes from the LIPS dataset, and on the standard Gaussian data, which you can see because they are synthetic and we construct them with such a way that the optimum mini-batch size is really faster than any other selection. And we have on top of this important sampling and other different variants that I will not cover in this talk, but I will be happy to discuss later in more detail. And we have also, just briefly, we have also a decreasing step size results where we show where you need to stop having a constant step size and you need to move to the decreasing step size. And to the best of our knowledge, it was the first time that it was shown the point that you need to change in terms of iterations, that you need to change from the constant to decreasing step size. And we have experiments that verify exactly this theoretical result, that if you run your method, and this is the regime switch, the one that we are proposed, the red line. If you run the constant step size, you achieve the neighborhood of conversions that I mentioned before, and then you start using the decreasing step size, then you can find the optimal solution. And all of these results, again, hold for any sampling strategy that, that exists at the moment and any reasonable distribution D. Okay, having said that, let's move to the second part. I feel more excited at the moment because I'm very interested on adaptive methods and methods that does not require any tuning in order to guarantee conversions. And this is where this work on stochastic polyak step size of AGD comes where it belongs. So a classical conversions analysis of AGD, and this is also the case of the previous part of this talk, requires quantity like L smoothness and mu strong convexity. These quantities, these parameters require in order to find what is the best step size or what is the best momentum parameter if you have AGD with momentum. And in several practical scenarios though, these values are unknown. You might find it, for example, in strongly convex in logistic regression problems, but let's say that we have a deep neural network, that everything are unstable and we don't have any information about exactly these values, how we can evaluate it. And at the moment, there are two solutions. The first one is to try a trial and error procedure to find the best parameter. Do a grid search and find what is the best step size, what is the best momentum parameter, and use it. However, this is very time consuming. And at the moment, there is also a different line of work, which is the one that you select the step size or any parameter of the method in such a way in order to be parameter free. Don't care about the properties of the problem. And there is rich literature on adaptive methods. However, it was shown recently that especially variants of Adam that is used in deep neural networks might fail to converge to an optimal solution even for simple problems. And this is why we, in the first place, tried to come up with a whole alternative compared to this line of work. All of these variants of Adam or rectified Adam, RMSprop, use similar step sizes. To a solution of this or an alternative to this, we propose the SPS optimizer, which is a stochastic polyak step size that I will now present. We provide, in this work, we provide a novel adaptive linear for AGD, which is a stochastic polyak step size, and it can be seen to be a stochastic variant of the classical polyak step size that proposed by Polyak for the gradient descent. And we argue that this is an attractive choice for typical machine learning applications. We provide convergence guarantees for AGD with SPS for strongly convex, convex, and non-convex smooth functions. We do not require any additional unnecessary assumptions similar to the previous line of work that I already presented. By doing that, we provide a novel analysis for constant step size AGD. For the over-parameterized models, when all the component functions Fi has the same solution to the original problem, to the general problem F, then we can guarantee fast conversions to the true solution, similar to the deterministic gradient descent. And we make extensive experimental evaluation of the AGD with SPS, and we show its strong performance, compare it with standard state-of-the-art optimizers that at the moment used for training neural networks or other over-parameterized models. Now, let me go into the details of what is the stochastic polyak step size. So the deterministic polyak step size, as I mentioned before, proposed by Polyak in the 80s, and is in the update of the gradient descent, Polyak suggested to use the step size which is the ratio of the function suboptimality over the norm of the gradient evaluated at iterate xk. This might seem strange because it requires this f star, the optimum solution of the original problem. However, as Polyak argued and many following up papers, there are several applications that this is known. The most prominent that I'm aware of, and I use it in several of my applications, is the convex feasibility problem, where this f star is equal to 0. And what we did is that we took these ideas of the deterministic Pollack stepsize proposed in the 80s, and we move it to now. And we propose the stochastic Pollack stepsize. So in its simplest form, let us see again the update of AGD, where it selects only one single component Fi and evaluate the gradient of this single component in each update. So what we're suggesting is the SPS, the stochastic Pollack stepsize, is the ratio of the function suboptimality of the function Fi, the one that you are selecting in your gradient, and the norm of the gradient evaluated at iterate xk. And we provide also a conservative variant of it, where it does not allow the stepsize to become very large. The reason for doing that is because we noticed that in deep learning experiments, this very large step size, it was prohibitive because it was overfitting the data that we are trying to have. Note that SPS and SPS max, the two variants of our stochastic Pollack step size, do not require the L smoothness or the mu strongly convex parameter to go and define them. However, they requires the knowledge of the Fi star, which, as I defined earlier in the talk, we have it to be the infimum of the functions Fi. However, as we will argue, this Fi is known for typical losses that appears in machine learning. Here, C is not a parameter that needs to be tuned. Theoretically, if, for example, you have a strongly convex problem, this C is equal to half. If you have a convex and non-convex problem, this C could be equal to 1. The gamma B is a bound that keeps the SPS small, as I already mentioned, and is the one that defines how small will be the neighborhood of convergence. So we evaluating Fi star because that's the main question that one could ask. How is it possible to know this Fi star? And for standard and regularized surrogate losses that appear in machine learning, like square loss, logistic loss, exponential loss, or Hedge loss, the infimum of the Fi is always 0. So you can simply use it without do any computation. When you are now in the regularized case, you can also evaluate it efficiently using Lambert W functions or the R Lambert function. I will not cover this in this talk, but this is very simple closed form expressions of the Fi star, which can be evaluated without running any algorithm. You have a closed form expression and you use it. And we provide several convergence guarantees. I will not provide theorems here, but I will provide a table to explain what we have. We have 4 classes of problems: the strongly convex, convex, non-convex that satisfy the weak growth condition, and functions satisfy the Pollack-Loizo condition. This can be seen as a condition that that functions have when all local minima are also global. And here we have the standard quantities for these classes of functions. For example, for strongly convex and PL functions, we can guarantee linear convergence to a neighborhood that is proportional to the upper bound on the Pollack step size and the sigma square. And for convex and non-convex function, we can guarantee with sublinear convergence to a neighborhood that is again proportional to this upper bound on the SPS max. Here, we need to highlight that all of our convergence analysis require a different assumption. And the one is this one here. So our sigma is not the standard sigma that is used in most of the AGD analysis, where we have the norm of the gradient to be bounded or the norm of the gradient at the optimum to be bounded. We went and we defined the sigma here to be the objective difference at the optimum point. And we assume that this is finite. Note that when we have over-parameterized setting, then this sigma is equal to 0. So because that's a definition of overparameterization, that all of FIs have the same optimum value compared to the original function f of x. And also it holds that this first part of the Pollack step size, this one here, the ratio, can be lower bounded by 1 over 2CL max, which means that if we select the upper bound to be less than this lower bound, then we have for free an analysis of the LGD with constant step size. And we can provide tight convergence results and match the state of the art at the moment also for the LGD with constant step size. Having presented now the theory, let me show some experiments on first synthetic and then deep learning experiments. So we have the logistic regression problem, which is a standard one that I believe we are all of us familiar with. We have the finite sum structure, and we have the logarithmic of 1 over e minus biaix. This is exactly the expression of the logistic regression, and we have the regularized L. If you have a lambda to be equal to 0, then you have unregularized case. And here in this experiment, we compare LGD with SPS with the constant step size LGD. And we note that in order to have convergence guarantees for the LGD with constant step size, we require a lot of tuning in order to have a reasonable convergence to a neighborhood and a reasonable fast convergence. However, for the SPS, here I have the SPS with upper bound 1, 5, and 100. We note that the behavior in practical scenarios is exactly the one predicted by the theory. The neighborhood increase as the upper bound of the SPS max increase. Here we evaluate the Fi star to be 0 when we have unregularized logistic loss. And for the regularized one, we have Fi star evaluated using the R-Lambert functions. And for the multi-class classification using deep neural networks, we run the method on the standard setting on CIFAR 10 and CIFAR 100 on ResNet 34. And we note that the training loss, in terms of training loss, LGD with SPS, which is the red line, is faster than any other state-of-the-art optimization method. Here, SLS is a recent stochastic version of the line search. So, however, I need to highlight at this point that the line search requires this expensive backtracking step. You need to have a condition that needs to be satisfied in each step, and you need to check that. It turns out that sometimes it's even 4 or 5 times more expensive in each iteration compared to our HDD with SPS. In terms of validation accuracy, it is competitive compared to other state-of-the-art methods for solving these two kind of problems. And another interesting observation is that the step size of LGD with SPS first increase and then decrease to a constant value, which normally people that training deep neural networks, they force the step size to have this behavior. However, with LGD with SPS have this behavior for free. We do not have any explanation of this theoretically. It just turns out to be the case in all of the experiments that we tried. And now we try to understand what is happening behind that. But it's really surprising and has a really good performance in all of the datasets that we tried it. So as a summary about this part of the talk, we propose and theoretically analyze the stochastic variant of the classical Pollack step size. We explain why this is an attractive choice for LGD, because the Fi star is equal to 0 for most standard surrogate losses, or can be easily evaluated in the unregularized case. We show the strong performance of LGD with SPS compared to state-of-the-art optimization methods. And at the moment, I'm working on understanding how this can affect the momentum method. If on top of the SPS we add momentum, what will happen? How it will behave compared to, let's say, Adam, that have some convergence guarantees for the momentum variance? What will happen for non-uniform samplings? And what will happen if we use SPS on distributed setting? So I think in terms of time, I don't have a lot of time to go into the Hamiltonian games. I can cover that just briefly, just give one slide of what we did to get the main idea, and then I will go to the conclusion and future research direction. So the problems that we're trying to solve is the min-max problems that have a finite sum structure. This is normally the problems these problems appear on domain generalization, on generative adversarial networks, and different adversarial formulations in machine learning. So what we did is that we went and we make some assumptions on this problem, and we reformulate it as a finite sum optimization problem. And by doing that, we show that the solution set of this problem, the Nash equilibria solving this problem, are equivalent with the solution set of a finite sum optimization problem of n squared components. And this, by doing that, we were able to use for free any stochastic optimization method that we know that solve finite sum structure problems in order to solve this problem here. I will skip all the details and I will go to the future research directions. So I'm good on time, Jeff? Do I have another 3-4 minutes?
Perfect. Yeah, you have about 3 or 4 minutes. That's perfect. Yeah,
That's
5
perfect.
minutes for
Okay.
questions. Yeah.
Yes. So I'm planning to continue working on stochastic optimization methods for machine learning and deep learning. In particular, I'm very interested on adaptive methods, methods that are parameter free and can guarantee, and we will be able to guarantee good performance in general setting, mainly convex and non-convex optimization problems. I'm interested to extend previous results that I had that appears in 2 journals in 2020 that focus on linear systems and convex structure quadratic optimization problems, and try to extend these 2 results on general convex and non-convex problems with goal to obtain faster accelerated methods in the stochastic setting, either using momentum or in exact updates. I'm interested to propose optimization methods that have as a focus the deep learning setting, how we can design optimization methods that work better for specific architecture of deep neural network, or answer the other way, the opposite question, that if you have this optimizer, how you can construct a deep learning architecture in order to make it obtain better generalization performance. At the moment, most people use Adam for all of the, or AGD with momentum, for all of the standard architectures in deep neural network. But the question, let's say if we focus on AGD with SPS, can we construct an architecture of deep neural network such as this method in combination with AGD with SPS will have better performance? I'm interested on adversarial formulation in machine learning, which can be seen as game theory formulations, in particular on understanding dynamics of differentiable games and develop the methodology that will later guide us in designing algorithms with convergence guarantees for solving these problems. This appears in several applications, and the one that I'm mostly interested in are the generative adversarial networks. I will be very interested to continue working on distributed and decentralized methods for solving convex optimization problems and training deep neural networks. My goal in this direction is to reduce the communication cost by combining different tricks like compression, having local updates, asynchronous protocols. I have several papers towards this direction, and my goal is to use these ideas on randomized gossip algorithms and distributed and decentralized protocols to extend them to the most challenging task of training deep neural networks. And of course, the federated learning, where is a recent setting proposed only in 2017, where we have the clients where collaborative train a model under the orchestration of a central server. Here, the clients can be mobile phones or a whole organizations, and central server can be a service provider. However, the challenging part is that the training data are decentralized. The nodes, they don't have the same data. This, I believe, if we developed efficient, fast and reliable federated learning algorithms, could have potential huge impact in the society. And already these federated learning ideas using several applications in Google, Apple is using Gboard mobile keyboard, for example, in Apple, in Hey Siri and other applications. But the one that I'm most interested in are the medical research, where federated learning could have potentially a lot of application in pharmaceutical discovery, electronic health records mining, and medical data segmentation. And towards this direction, in an ICML paper of this year, of 2020, last year, we provide the tightest convergence analysis of local SGD, or the Fed averaging, which is probably the most prominent federated learning algorithm. And we did that under the weakest possible assumptions. And that's the 4 directions of research that I'm interested to pursue. And I did all of this research with these amazing collaborators from industry and from universities. And thank you very much for having me. I will be more than happy to answer any question.
Thank you very much, Nicholas. We do have a few minutes for questions. I'm seeing tons of applause, so good job by you. Are there any questions for Nicholas? Maybe
I had a question.
Go ahead, Rob. Yeah,
Rob here again. Yeah, I was wondering if you just go back to the min-max problem and just say a little bit more about the
Yes,
concept,
I will be happy.
like in terms of what is what kinds of properties does that function have that you're optimizing, the G's, and then what are the results? Yeah, sorry.
Yes, yes.
Thank you.
So, of course, so we have the stochastic smooth game. This is what we call it, but it's a classical min-max problem from optimization viewpoint. And we assume that this function is a finite sum function, and we assume that this is smooth, both in terms of x1 and in terms of x2. We assume that it's twice differentiable, and we also make the assumption that this problem has at least one Nash equilibria, and also that that any stationary point is a Nash equilibria. This is what we have as an assumptions in the original problem. And our goal is to find this min-max solution of Nash equilibria. And what we did is that as just a main contribution, briefly, what we did is that we provide the first global non-asymptotic last iterate convergence guarantees. All of the convergence guarantees for this kind of problems, it is not last iterate, which is important property to have in mind when you need to guarantee convergence in this min-max setting. All of the previous results require averaging of iterates or averaging of all points that either you see or you will see at some point. And we provide the first convergence guarantees of a second order method. The stochastic Hamiltonian methods that we proposed are second order methods. And in order to do that, we come up with a novel unbiased estimator of the Hamiltonian function, which I will go through it in the next slide. And we provide the first stochastic Hamiltonian variance reduced method. We combine SVRG type of methods from optimization literature with a Hamiltonian viewpoint. And as a main takeaway message is that we show that through the Hamiltonian perspective, we are able to use any popular stochastic optimization algorithm to solve these stochastic minimax problems. And what we did, as I explained before, we start from this problem with all of these properties that I previously mentioned, and we reformulate it as this finite sum structure Hamiltonian function. The reason that we call it Hamiltonian is because this is what it was known from the physics part, that using this kind of methods, but nobody did it in the stochastic setting. And we run, in each step, we require the evaluation of this stochastic component, the gradient of this stochastic component Hi and J. Here, Hi and J depends on this psi I, xi and j, where is the vector, the sign vector of the gradients evaluated in terms of player x1 and player x2 of each component gi. And what we did now, and that's the most important, is that we went and we construct, and we found what assumptions this Hamiltonian is satisfied. And I will not go into the algorithms. The one is a classical AGD and the other is as variance reduced. But what we show is that for the stochastic, we have two classes of games, stochastic bilinear game and stochastic sufficiently bilinear game. This is a class of non-convex, non-concave games that it can be seen is, if you are familiar with what it is the Polyak-Loizo condition in optimization literature, it can be seen something like that, but for games. And what we did is that we have these two classes, and we show that for the stochastic bilinear game, the Hamiltonian function is a quasi-strongly convex Hamiltonian, which probably answer also the question that Kartik asked before about what is the simple example of a function that satisfies quasi-strong convexity instead of strong convexity. And this is exactly one example to answer his question, that for the bilinear game, we went and we showed that the Hamiltonian is quasi-strongly convex. And for the sufficiently bilinear, we went and we showed that satisfied the Polyak-Loizo condition. And by doing that, and show as well that it's a smooth function, we were able for free to use stochastic gradient descent, either with constant or decreasing step size, and variance reduced methods, either with or without restarts. And just to show you an example of a very simple game, the stochastic bilinear game. This might look simple, but there was no method at the moment that converged for this problem. There is no known method besides our paper that has convergence guarantees. It appears only 1 or 2 months ago, after our original paper, some other modifications that they guarantee convergence, but before our ICML papers, this was an open problem. So what we did is that we ran the Hamiltonian method. When I say Hamiltonian, I mean AGD on, let's say, the Hamiltonian function. And we ran that, and we show that we can have convergence guarantees for this problem. And what is impressive is that if we see the vector field, all the other methods that either diverge, for example, the stochastic gradient descent ascent diverge. You start from this point and you go outside of the solution. There is one method, this SVRE, that converge, but without convergence guarantees, this brown line, but this suffers from these rotations that normally appear in min-max problems. However, using this Hamiltonian viewpoint, we were able to find exactly the conversion. There is no rotation, there is nothing. You start from the point and directly you find the min-max solution, the Nash equilibria, with any of our method. For example, if you are from an optimization viewpoint, it behaves exactly as you expect to behave. With constant step size, you can converge to a neighborhood and play around to a neighborhood. That's the reason of the orange part around the solution. And the other one, the decreasing one and the variance reduced one, goes directly to the solution without any issue. And that's a brief.
Yeah, great. Thanks. That's very impressive. I will look forward to taking a closer look. Yeah, very cool.
Thank you. Thank you very much for the question.
Excellent. So we're just a few minutes over, so I'm going to just respect the people's time and just want everybody to thank Nicholas again for a wonderful talk. Some of us probably, maybe we'll take we'll let Nicholas take like a 2 or 3 minute break. Could take a drink of water, and then a few of us, maybe if you still have additional technical questions, but actually even more important, if you just want to just chat with Nicholas and try to convince him what a great place Madison is to live, especially compared to Cyprus, or certainly compared to Montreal, then you can feel free to hang out. But like maybe I'll just take, I know I need to go fill up my coffee mug, so maybe we'll just take like a 2 minute or a 3 minute break. We'll reconvene back at 10:38 for people who still want to just chat with other people who want to chat with Nicholas now. Yeah, and Jane, you can stop the recording if you want. You don't need to hear us chatting with him. But I'm going to take a short break. And Nicholas, I encourage you to as well.
Thank you very much. Thank you very much, Guy.